we're going to be doing is looking at some trends on the periodic table. And one of the trends or patterns that we're going to be looking at is the size of the atoms, what we're going to call the atomic size. One of the things that we will find out about atomic size is that as you move down a column, a typical pattern will occur. And as you move across a row, another pattern will occur. So the first thing that I would like to do is look at what happens for the trend of the size of the atom as we move down a column, and what happens to the trend as we move across a row, and then why that occurs. The first one I would like to do is take a look at just one column and see what happens to the structure of the atom. So if we look at everybody in column 1A, what I want you to notice is if we start at the top left for column 1A, we start with one proton and one energy level with one electron on the outside of that energy level. That there is a hydrogen atom. If we go below hydrogen and look at lithium, lithium has 3 protons on the inside. And then lithium has not just one energy level, but 2 energy levels. If we go down to the next element below lithium, sodium, sodium has 11 protons. 11 protons, and because it's in row number 3, it's got 3 energy levels. So what happens to these atoms, what happens to the atomic size as you look at this trend or pattern going down a column of the periodic table, I think you can see that the size of the atoms begins to increase as you move down a column. And the reason it increases is because as you move down that column, each successive element, you are increasing the number of energy levels. So as you go down a column of the periodic table, or down a group or a family of the periodic table, because you are adding energy levels, those atoms continue to get bigger. Yes, Jose?
Is it more valence electrons every time you go over, like to the right?
Every time you move from column 1A to column 2A, now you'll have 2 valence electrons.
Like more every time?
And then, yes.
All right.
All right. Now, what I would like you to do, on that R6 that I gave you, the atomic radius chart, what I would like you to do is outside the periodic table. I know you have a column, you have your periodic table set up, and you got a 1A here, and you have some margin out here. What I would like you to do is I'd like you to write an arrow pointing down, indicating that as you move down a column, this is what happens. So for the atomic size, we will write an arrow going down, and we will write increasing atomic size. Increasing atomic size. Now underneath, what I'm going to do is I'm going to write why that happens. The reason it increases as you go down is you are increasing the number of energy levels. So you're increasing the number of energy levels. And that seems straightforward based off of what we've learned about the structure of the atom. As you go down a column, it should get bigger because you get more and more energy levels. The atoms should get bigger. That makes sense. Now, here's what's a little bit difficult. What you will notice is as you go across a row of the periodic table, so we're going to draw an arrow going that way. As you go across a row of the periodic table, you see a very different trend or a very different pattern. As you go across a row, typically what happens is you get a decreasing atomic size. As you go across a row, you get a decreasing atomic size. So let's say that I took a look at sodium with its 2 electrons here, its 8 electrons here, and 1 electron here. As I go across sodium's row and I end up way over on the other side for argon, what happens is argon's got 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 protons. And it still has 3 energy levels. But as you might expect, argon would be bigger than sodium because it's got 18 protons and 18 electrons. But if we looked at the data on our R6, that is opposite of what we would expect. Even though they are in the same row, they have the same number of energy levels, even though argon has more protons and more electrons, the size of argon is actually smaller than sodium. And the reason it's smaller is, in this same area of space, in the same number of energy levels, you are now packing more protons and more electrons into that same area of space. As you know, positive protons are attracted to negative electrons, and so what happens as you go across a row, it's more positives and more negatives, they start squeezing in on each other because they're attracted more. 11 protons and 11 electrons are attracted to each other less than 18 protons and 18 electrons. So the way we will describe that is we will say more protons and electrons at the same energy level. Therefore, greater attraction for the electrons to the protons. So because of that, the atom actually squeezes in on itself. As you go across a row of the periodic table, 3 energy levels, or 4 or 5, as the energy level stays the same as you go across a row, you're packing more positive protons in the nucleus, more negative electrons in the electron cloud, and it actually squeezes in on itself. It actually gets smaller. Okay? So 2 trends for atomic size: increasing down a column, decreasing across a row.